All right, I have hit recording.
Fabulous. Welcome everyone to our, which lecture is this? Third?
Third lecture. That's
Our
right.
third Brain Bee lecture. If this is your first time tuning in, my name is Jordan. I am the vice president of the Mayo Clinic Brainwaves organization that's putting on Brain Bee. And Sebastian, do you want to introduce yourself?
Hi, my name's Sebastian, and I am also not part of the Mayo Clinic, but the University of Central Florida, and I've been working very closely with Jordan and Gabby and the BrainBee team for starting this new chapter. So let's get to it.
We are very excited. We're going to go over chapter 9, 10, and 11 today. I don't know that we'll hit all of it in the allotted time, but you guys should have the slides. Your teachers will have those and they can share them with you. And if you have any questions, please feel free to reach out about this chapter or any of the chapters that we've gone over so far. All right, so this first chapter 9 is about brain states. It doesn't want to click. Oh, and we're going to start by talking about sleep. We have a lovely sleeping friend here. So people spend a third of their lives asleep, which is kind of a terrifying factor when you think about how long you've been alive and how much time you have left. A third of that will be spent asleep, but sleep is super, super important. A huge part of our health is having good quality sleep. And have been studies done showing that I think the statistic is 11 days is how long a person can go without sleeping. It wouldn't be good for you or pleasant at all, but after 11 days, a lack of sleep does become incompatible with life. So sorry, my dog is barking. It's super important to get good and regular sleep, and not having sleep can lead to different health conditions such as diabetes, obesity, high blood pressure, anxiety, and depression are all related to chronic sleep deprivation. And, one thing that sleep researchers will talk about is good sleep hygiene. So when we say, hand hygiene, we're talking about washing our hands well. When we see sleep hygiene, we're talking about sleeping well. And good sleep hygiene, the thing that my sleep science professor always liked to tell me in college is that your bed is only for sleeping in. So, hanging out in your bed, playing video games, reading books, watching movies, doing homework, anything that's not sleeping should be done out of your bed. You shouldn't be eating in bed. You also shouldn't be using electronics right before you go to bed. It's important to have a calm kind of wind down to going to bed, not have any bright lights or noises going on while you're sleeping, and to try to not use your electronics for at least an hour before you go to bed. Now, I'm not saying that I stick to any of those rules. I love reading in bed, and I definitely have been known to scroll on Instagram before going to bed. However, if you're having trouble sleeping or staying asleep or things like that, the first thing a doctor will tell you when you talk about is how's your sleep hygiene, and that's kind of what they're referring to. So, brain activity during sleep is very interesting, and one of the ways we study this is using electroencephalography. And when you have an electroencephalograph done, they can do it a couple different ways. Sometimes they'll give you a cap that they put on that has the electrodes all tied into it, and other times they'll go in and they'll individually adhere the electrodes to your scalp, and they put some nasty goo on your head that's going to make your hair all crusty afterwards. And what that does is it helps create a connection between your scalp and the electrodes so that the electricity is conducted better and then we get a better read. Um, elec the electrodes are going to record and detect the net electrical activity of cortical nerve cells and the net electrical charge produced when neurons increase and decrease their activity as a group. And so in an active neuron, ions are moving in and out of the cell, and this is going to alter the electrical charge across the cell membrane. And the electroencephalograph, in theory, is going to pick up that charge and record it, and it'll give us a nice printout of a graph with the different signals on it and corresponding to different brain waves. So here we can see some of those brain waves. If this was a real electroencephalograph, there'd be many more lines. There'd be a line for every single electrode on your scalp, and they each would have different shapes and sizes. And so they'd have different amplitudes, which is going to be the height of the wave, and different frequency, which is how many waves. So brain waves tend to be cyclical, and they correspond to the rising and falling of brain activity. And we can detect the result of electroencephal, or we can detect the result of brain activity using EEGs. And EEGs can be very important, can be used to detect brain function and tell us a lot about what's going on in the brain. So one area that we often see EEG used is in epilepsy monitoring. So if you've heard of epilepsy, then you've heard the term seizures, which refer to aberrant bursts of electrical activity in the brain. And in order to diagnose someone with epilepsy, there has to be a documented seizure. And that doesn't necessarily always mean it needs to happen with an electroencephalograph recording. But oftentimes, if doctors are having difficulty determining whether or not a patient is having real seizures or pseudo seizures, so whether the symptoms a patient is experiencing are from these aberrant bursts of electrical activity, or if there's something else going on, they'll do an EEG on the patient, and sometimes they'll do extended EEG. So someone might have to wear an EEG cap for 24 hours to up to a week or a couple of weeks. And so to give the doctors a long enough period of time for a seizure or that seizure-like activity to occur, and for them to make a determination on whether or not the patient does have epilepsy. So there's two main states during sleep. We have slow wave sleep, which is high in amplitude, low in frequency, and then rapid eye movement sleep, REM, low amplitude, high frequency. And the reason we call it REM is because if you've ever walked up on someone who's in REM sleep, you'd know it because their eyes will move rapidly beneath their eyelids, and you'll see kind of a twitching on the external eyelid. So here we have a graph of slow wave sleep. It has the high amplitude, low frequency waves, and it indicates that many cortical neurons are switching their activity in a synchronized way. So they're going from depolarized to hyperpolarized and back again, but they're all doing it together. Slow wave sleep is super important for sleep function. Oh, the longer someone is awake, the more slow waves they experience in the slow wave state. And the longer they become less frequent the longer someone is asleep. So we're going to see, so if someone's super, super tired and hasn't slept a lot recently, then we'll see a large amount of slow wave sleep at the beginning of their sleep cycle. And as they sleep, we'll see less and less of the slow wave sleep. And if someone is awakened during this state, most individuals can recall fragments of their thoughts, but not full dreams. So here we have rapid eye movement sleep, the type of sleep that's easily recognized by looking at someone and watching their eyelid movement. And so rapid eye movement sleep, or REM sleep, has low amplitude and high frequency waves. So we can see that the waves aren't reaching up very high, but there's a lot of them. And the reason for this is because the neuron activity isn't very synchronized. So some cells are depolarizing while others are hyperpolarizing, and the sum of their electrical activity is less positive than if acting in synchrony. And the best way to kind of visualize that is if you have 100 people running in one direction, then the net amount of people going in that direction is 100. But if you have 50 people running in one direction and 50 people running the opposite direction, then the net movement in our original direction is 0, because they cancel each other out. So it's that same idea where the overall sum electrical activity is less, even though the amount of electrical activity is not less. The cells' activity are kind of canceling each other out. And so brain activity during REM sleep looks very similar to brain activity when we're awake. There's a lot of different things happening at once. And the neurons of our motor cortex fire as rapidly as they do during waking movement. This is also when dreaming occurs. And oftentimes people have atonia, or loss of muscle tone, causing the body to become temporarily paralyzed, with the only muscles remaining active for those enabling breathing and eye movement. Some people actually do have conditions which cause them to wake up during REM sleep, and they'll have what is called sleep paralysis, where they wake up and they're completely unable to move. And the reason for that is that your body paralyzes you while you're sleeping so that you don't injure yourself. And some people have aberrant paralysis, where they're paralyzed even after they wake up, and other people lack that paralysis. And sometimes the way that manifests is people will sleepwalk or move around a lot in their sleep. It's not letting me click. Okay, here we go. So this is just a little bit more about the different periods of sleep and how REM and slow wave sleep switch on and off as we progress throughout our sleep cycles. So here's another fun kitten friend, and we're going to talk about some sleep regulation. So this is the arousal system, which maintains wakefulness, and the neurons in this system connect with the forebrain using the neurotransmitters acetylcholine, norepinephrine, serotonin, and glutamate. And the neurons located in the hypothalamus produce orexin. And the location of this arousal system is mostly in the upper brainstem. We have our brainstem. Oh, I'm not using a pointer. Let's see. Can you see me pointing?
Yeah, I can see your cursor.
Fabulous. Here we have our upper brainstem. Okay, so orexin, that's the neurotransmitter we just talked about, and we've discussed neurotransmitters. I believe in our first lecture, we went over neurotransmitters. So if you have any questions about those, make sure to go back and review those lecture slides and then reach out if you have further questions. But orexin is produced by the hypothalamus, and it projects. So the hypothalamus sends this neurotransmitter out to the brainstem and spinal cord, thalamus and basal ganglia, forebrain, amygdala, and dopamine producing neurons. And there's two types of orexin. This neurotransmitter increases metabolic rate by activation through insulin-induced low blood sugar, which is involved in energy metabolism and preventing the sudden transition into sleep. And it also connects to the hypothalamic neurons within the neurotransmitter histamine. And histamine plays a role in staying awake. And so when I think of orexin, I actually often think of narcolepsy, because dysregulation of orexin is related to narcolepsy, which a lot of people I'm sure have heard of this condition. Have you ever heard of, someone who falls asleep randomly throughout the day and can't stay awake? This condition is often popularized in movies or cartoons or, in the media. People will talk about it because most people can't imagine having it, but where you're suddenly awake one minute and you're passed out in the next. And one part of that condition is orexin dysregulation. So the balance of neurotransmitters is super important, like I just said. In order to maintain your sleep and wakefulness states, you need to have the right amount of neurotransmitters, including orexin. So acetylcholine and norepinephrine, two other neurotransmitters, are in high amounts when we're awake and low amounts when we're slow wave sleep. And then when norepinephrine is low but acetylcholine is high, we're in REM sleep. And so these neurotransmitters activate the thalamus and the neocortex enough for dreaming to occur. And then we have this statement that forebrain excitation without external sensory stimuli leads to rapid eye movement and suppression of muscle tone. That suppression of muscle tone is the atonia we were talking about earlier, the paralysis that occurs during sleep. So here we have the ventrolateral preoptic nucleus, which is a group of nerve cells in the hypothalamus, which release the inhibitory neurotransmitters galanin and GABA. So GABA is the major inhibitory neurotransmitter, and glutamate is the major excitatory neurotransmitter. And a great way, or one way I remember glutamate, is because glutamate's symbol is the letter E for excitatory. So the main function of this nucleus is the active suppression of the arousal systems that keep us awake during slow wave sleep. So basically, your activation or arousal systems are constantly functioning, or would be constantly functioning if something else didn't turn them off. They're not going to stop on their own. And so this nucleus is almost like a stop sign or a red light. So, it keeps the cars from going forward, but they would not stop without it. And so damage to the VLPO nucleus causes irreversible insomnia because there's nothing keeping the activation or arousal system from running all day long. So sleep-wake cycles, super important. If you have ever been to sleepaway camp or, had several days where you stayed up super, super late, you might have found that you started to reverse your sleep-wake cycles. I found returning one summer from college that I completely reversed my sleep-wake cycles after finals week and a lot of late nights. And my body wanted to go to sleep at 4 a.m. and wake up at 4 p.m., which was not fun and very much not fun to reverse. So it's really important to maintain good sleep-wake cycles and go to bed at a reasonable hour and get up at a reasonable hour and then stay awake throughout the day. So our circadian system tells us what time of day or night it is, and our homeostatic system tells us how long we've been awake. And so these are separate systems and they act independently. And activating the brain's arousal system can oppose these systems and keep one awake long after long periods of wakefulness. So we can subvert our homeostatic system and, force ourselves to stay awake longer and longer. But it's not good for you. So here's our circadian timing system. And it's regulated by the suprachiasmatic nucleus, which is a small group of nerve cells in the hypothalamus that act as a master clock. The suprachiasmatic nucleus sends signals through the brain regions connecting to the VLPO, which we discussed, and the orexin neurons in the lateral hypothalamus, directly regulating arousal. Cells express clock proteins that go through biochemical cycles of around 24 hours, and they set the pace for daily cycles of activity, sleep, hormone release, and other bodily functions. These cells receive input directly from the retina of the eye, adjusting the master clock to the outside world's day and night cycle. You guys should know a decent amount about the retina. We went over the eyeball during, I think, our first lecture series. So again, if you have any questions about that, please refer back to those lectures and then send us questions if you still have them. Here we have our homeostatic system, and this causes one to feel sleepy if they stay awake longer than usual. Adenosine levels in the brain increase and bind to specific receptors on the nerve cells and the arousal centers to slow cellular activity and reduce arousal. And so the way it was explained to me is that your body is a lot like one of those little sand timers where it slowly trickles down. And then we have our body that pumps, the longer we're awake, the more adenosine is pumped into our system or produced. And then when that adenosine reaches a certain level, it, flips the system almost, is how it was once described to me by my sleep professor, and activates all of the systems in our brain that encourage us to go to sleep. So the VLPO and the orexin system and all of these systems are activated by these heightened adenosine levels. So caffeine, something that many, many people love, the way it works is it binds to the adenosine receptors throughout the brain and prevents their interaction. And so adenosine, even though your body is continuously producing it, caffeine interferes with the binding between adenosine and its receptor and prevents it from instigating those sleep-like effects. So sleep disorders, REM sleep behavior disorder, unknown cause, when nerve pathways in the brain prevent muscle movement during REM sleep malfunction or do not work. Common in individuals with degenerative neural diseases such as Parkinson's, strokes, and other types of dementia. Symptoms are sleepwalking, getting up and acting out one's dreams in the real world while still asleep. And then there's a couple different treatments. So one of them is drugs that we use for Parkinson's syndrome. Other options are the drug clonazepam, which enhances the effects of the inhibitory neurotransmitter GABA. So this is what I was talking about earlier when I mentioned that, your body is supposed to be paralyzed during certain portions of your sleep. And when that doesn't happen or when that goes awry, people sleepwalk or they act out during their sleep. And this is the written out example of that. Insomnia, difficulty falling asleep or difficulty staying asleep. So a lot of people think that insomnia is just related to the beginning of sleep when we're going to bed. But if you're able to fall asleep easily but unable to stay asleep throughout the night, that is also considered insomnia. Daytime sleepiness one cause of this is sleep apnea. So sleep apnea is a condition where the systems in your body that mainly in your, let's go back to our diagram. So here we have the lower part of your brain stem, which has your medulla and your pons, and your major structures that are required for keeping you alive. And so sometimes this area is referred to as the reptilian brain because it's very, very old, and all of these structures are essential for life. So they're involved in all of the functions in your body that we don't think about. And sometimes they go awry and they don't act as they're supposed to. And one of those conditions is sleep apnea, where your brain forgets to breathe while you're sleeping. And so one result of that, if you don't have severe sleep apnea, is that you'll wake up frequently throughout the night because your body jerks you awake because you've stopped breathing while sleeping. Then you have excessive sleepiness during the day. And if you've ever heard of a CPAP machine, which it has a mask and then there's tubing connected to it and a little machine that sits in the corner, some people have to sleep with those at night, and in order to prevent them from stopping breathing through the night and passing away. And so CPAP machines are used as a treatment for sleep apnea. So here we have, this is typical breathing during sleep. And then we have a blocked airway. So here's another cause of sleep apnea that is unrelated to your brainstem, has to do with the actual structures in your body. And so this is a physical blockage of the airway into your body, but another cause can be malfunctioning in your brainstem, causing your brain to no longer send the signal to breathe. So air muscles of the throat relax during sleep to the point of collapse, closing during the airway, difficulty breathing during sleep, waking up without entering deeper stages of slow wave sleep. Risks are high blood pressure, increased risk of heart attack, and daytime sleepiness. And then treatments include focusing on reduced airway collapse during sleep, losing weight, avoiding alcohol or sedating drugs prior to sleep, avoiding sleeping on one's back, breathing machines, CPAP, or surgery to correct the anatomy in extreme cases. Narcolepsy, this is another condition that we mentioned earlier. Brain suffers loss of orexin neurons in the lateral hypothalamus that aid in controlling the transition into sleep. Causes regular cycling to be disrupted. The symptoms include sleep attacks during the day, causing the individual to suddenly fall asleep, entering REM sleep very quickly. So someone goes to bed and they're immediately in REM sleep. And hypnagogic hallucinating, entering dream states while still partially awake. I know this went viral on social media a couple years ago, people talking about this condition, and what it is when you're asleep but you're aware that you're sleeping or in a dream and you have some level of control within your dream, and that's a form of hypnagogic hallucination. But what they're referring to is when someone goes to bed and they're immediately in REM sleep having these vivid dreams, but their body's processes haven't, or their brain's processes haven't fully shut down and gone to sleep, and so they still have some partial consciousness left. And cataplexy, attacks of paralysis or loss of muscle tone while they're awake, triggered through emotional experiences or hearing a funny joke. Arousal. So we talked about our sleep wake systems. So we talked about sleep, and now we'll talk about wake. Arousal involves changes in the brain and body that provide motivations to do an action. They're important for daily interactions, fulfilling needs, reproduction, and avoiding danger. Level of arousal vary on a spectrum of low to high. Falling below a certain threshold causes the transition from wake to sleep. Under heightened arousal, such as anxiety, the above threshold cannot be reached and one stays awake. So here are some of our this is the catecholaminergic neurotransmitter biosynthetic pathway. So I hope you recognize some of these names, but this is how we work from tyrosine to epinephrine. And here are the intermediates. Dopamine. Hopefully you've come across him. Neurotransmitters and arousal. So specific types of neurons in the brain, regions involved in arousal release multiple neurotransmitters. These neurotransmitters tell the rest of the body and brain to be on alert. So earlier we talked about how the I believe the VLPO. Let's go back to that. The VLPO, part of its role is to suppress arousal systems that keep us awake during slow wave sleep. And so the VLPO actively works to suppress some of these neurotransmitters that are involved in keeping us awake and going. So types of neurotransmitters involved in arousal. Dopamine is a neurotransmitter. It's involved in movement. So if you've come across Parkinson's disease, one of the main topics of conversation in Parkinson's is dopamine, because in Parkinson's there's death to dopamine producing neurons in the substantia nigra. And I think the best way to remember this is that the treatment, or one of the earliest treatments for Parkinson's, was a drug called L-DOPA. So L-DOPA, dopamine. Norepinephrine, alertness. An easy way, I think, to remember norepinephrine and epinephrine is to think of EpiPens, which they give to people in the event of anaphylactic shock or, life-threatening allergies. And it's a shot of epinephrine directly into your system, and it jerks you awake. Serotonin has to do with emotion, and acetylcholine and histamine help the brain communicate with the body to increase arousal. Okay, so sensory input during arousal. Neurotransmitters provide internal signals that stimulate arousal. The outside world provides external signals that stimulate arousal. Examples include visual input, bright lights, auditory input, crowds cheering. The thalamus, aka the sensory clearinghouse. I like to also call this guy the train station of sensory. That's how I've always thought of it. As all of your sensory input comes in and passes through the thalamus and then gets sent out to the places it needs to go, except for our sense of smell, which bypasses the thalamus and goes directly to our olfactory centers. So one function of the thalamus is to regulate arousal. It receives and processes sensory inputs from important brain regions important to sensation, like vision and hearing, and then relays those inputs to the cortices. Autonomic nervous system. So part of our autonomic nervous system is our reticular activating system. You can see a lovely diagram right here. It's located in the brainstem. It controls the autonomic nervous system, affecting the heart rate, blood flow, and breathing. So these are all of those necessary functions that we don't think about, that are part of that reptilian brain, that need to be actively happening at all times. So you can see an eyeball right here, visual impulses, part of the reticular activating system. One thing to think about when we think about the brainstem is it's how important it is in keeping you alive, because it's in control of these very necessary functions. And one fun function of the brainstem is it has projections that are related to or it's close by to nerves involved in your ability to contract your eyeballs. And so if you've ever watched a medical drama, I'm sure they had this on the show, or if you've been in or around the medical field, you might have heard of the term blown pupil, and what that refers to is when someone's pupil is no longer reactive to light. And when physicians or other care providers see a blown pupil, they begin to get a little nervous, because a blown pupil could be indicative of a brainstem injury. And a brainstem injury is very serious, because if the systems that are involved in heart rate, blood flow, and breathing are affected, then there's a very little chance that the patient will be able to survive on their own off of machines. So our reticular activating system is essential for living. It controls the autonomic nervous system, affecting heart rate, blood flow, and breathing. Physical state of arousal brings important resources like oxygen and nutrients to where they are needed in the body. Coordinates signals coming from sensory inputs and the neurotransmitters, helps make sense of events in the brain, and pass information on to the rest of the body. So the importance of this system is that it enables an individual to be alert and focused. It aids in quickly processing information, allowing one to choose the appropriate emotional response or physical action for a given situation. Sexual arousal. So sexual arousal involves several complex brain systems. and the endocrine system. And when you hear endocrine, you should think hormone. Brain regions, neurotransmitters, and body systems are similar to those involved in general arousal. So even though this is a specific subtype of arousal, it involves a lot of the same players that we've previously discussed. So hormones set sexual arousal apart from general arousal. Hormones involve estrogen and testosterone. So those are two major hormones. Their function is to activate neurons that release the same neurotransmitters that are released during general arousal. Interactions with general arousal hormones, dopamine, serotonin, GABA, and glutamate. So all of these are neurotransmitters that we've previously discussed. GABA and glutamate are particularly important neurotransmitters because GABA is the major inhibitory neurotransmitter in the brain and glutamate is the major excitatory neurotransmitter in the brain. But all four of these are going to interact with your hormones. Brain regions involved in sexual arousal. So the brain regions that contain estrogen and progesterone receptors are the hypothalamus, amygdala, and hippocampus. The brain regions mediating feelings of reward and motivating sexual behavior, that's your nucleus accumbens. So we can see it in this lower picture here. And the brain region mediating emotions like pleasure and motivating sexual behaviors is your amygdala, which we can see right here. Attention. So attention is important for a long time ago when we were cavemen. Paying attention was important for staying alive, and these days it's important for succeeding and still staying alive. So making sure, we're looking both ways and before we cross the road and paying attention to what's going on around us is very important. Attention is a state of arousal that speeds processing and improves comprehension of environmental details. Focus. We have a lovely out of focus photo here. Focus and attention. Even with multitasking, it is impossible for the brain to process all sensory inputs. People focus their attention on one thing at a time. Attention allows one control and the ability to fine-tune one's focus to different locations, topics, and times. So this is a very interesting sentiment. So a lot of people claim to be great multitaskers, and I would like to say that those people are not multitasking, they're task switching. So one super interesting topic that I learned a lot about in college was the idea of task switching and multitasking. And multitasking doesn't really exist because it's quite hard for you to focus on two things at the same time. If you're an efficient multitasker, what you actually are is an efficient task switcher, which means you're able to quickly pivot between two things, but you're never actually doing or focusing on two things at the same time. So types of attention, voluntary or endogenous attention. So this refers to how and what we are choosing to focus on. And the brain regions involved are the frontal and parietal cortices, and we activate this when we control our attention or direct it towards a specific object or location. So involuntary or exogenous attention occurs when something in the environment, like a sudden noise or movement, grabs one's attention. So think of endogenous as we're exerting the control over what we pay attention to, and exogenous as something external is controlling what we're paying attention to. Exogenous attention involves distraction from our chosen goal, and the brain regions involved are in the right hemisphere, specifically the ventral frontoparietal network. Disorders of attention. Attention deficit disorder and hyperactivity disorder. I'm sure you've heard of this one. Schizophrenia, prosopagnosia, and hemi-neglect syndrome. So hemi-neglect syndrome is a super interesting disorder, in my opinion. Spatial neglect and unilateral neglect. Patients with neglect ignore the left side of their visual field and body and or individual objects. Damage to the right parietal cortex, which is important for involuntary attention. 50 to 82% of individuals suffering a stroke in the right hemisphere experience this. So if you are loving studying for the Brain Bee and want more material, I highly encourage you to read the book, The Dueling Neurosurgeons by Sam Keen. It's a really fun book, and I had to read it for my senior seminar during my last year of college. And one of the stories, or one of the things he talks about in the book, is hemi-neglect syndrome. And he talks about patients with hemi-neglect syndrome. And so when we think about hemi-neglect, what we often think of is someone ignoring their left side. So if you put a plate of food in front of them, they'll only eat one side of the food. If you ask them to name all of the things in the room, they'll only name half of the room, because even though they're visually able to see what is going on, their brain is unable to register the space. But what's really interesting is that sometimes that extends to memories too. And so a study was done in patients with hemi-neglect syndrome, and they asked the patients to stand on, I think it was a street in their hometown, and name all of the buildings on the street. And so the patients did it. And then they said, okay, in your head, turn around and name all of the buildings. I am so sorry. They asked the patients to turn around in their own heads and name all of the buildings. And in both instances, when they first asked the patients to name all the buildings and then turn around and name all the buildings, they only named the buildings on one side of the street because the hemi-neglect actually extended to their memories. Just kind of cool to think about. So this is the arrest system, or default mode network. So alert versus resting while awake. So here we can see activation of the default mode network and some of the areas it involves. During resting and relaxation, one usually avoids heavy thinking or complicated tasks. Default mode network is active. So if you are chilling on the couch, watching TV, not thinking about much, or if you've ever mindlessly scrolled through Instagram and realized that you don't remember the past 5 minutes, your default mode network is active. So even though you're not actually asleep, you're not alert. The default mode network turns on when one is ready to relax. Activity decreases when one starts doing or thinking about a demanding task. So as our alertness ramps up, the default mode network ramps down. Brain regions involved are the frontal brain regions, the ventromedial prefrontal cortex, the dorsomedial prefrontal cortex, and anterior cingulate cortex. Posterior cingulate cortex, lateral parietal cortex, and precuneus. It is also involved in brain regions with roles in emotion, personality, introspection, and memory. Here we have the ventromedial and dorsomedial prefrontal cortex. The ventromedial prefrontal cortex, you'll feel it when you have anxiety performing a task, and that which is suggestive of the default mode network's involvement in regulating emotion and mood. And we have the dorsomedial prefrontal cortex, which is involved in self-referential or introspective thoughts. It increases when an individual is at rest or dreaming. So if you ever zone out and start thinking about something you recently said, something you recently did, that's our dorsomedial prefrontal cortex at work. Okay, here's some posterior brain regions involved in the default mode network. The posterior cingulate cortex, lateral parietal cortex, and precuneus. These become more active when we're remembering concrete memories from past experiences. So here is the hippocampus, which is also part of the default mode network. It becomes more active when a person is at rest in the evening, and it becomes less active when waking up early in the day. This is indicative that the default mode network helps to process and remember the events of the day. So the fact that the hippocampus is more active at night rather than in the morning, and its involvement in the default mode network points to this idea that the default mode network is kind of like part of our shutting down routine of collecting our thoughts for the day, resting, and zoning out. Oh, I think this might be our last slide. Sebastian?
I'm here.
Hello?
Can you hear me?
Do we want to? Yes, I can.
Cool.
I'd say, are there any questions, but it's just us. To all of our lovely watchers at home, if you do have questions, please feel free to reach out. Your teachers have our contact information. And you should have access to these PowerPoints.
Mhm.
Are we ready to, how long was that?
I don't know if there's an exact time frame of the recording here. Do you want me to stop it or do you want me to do my part and then just put it all as one?
Let's put it all as one.
Okay, so I'll continue then. So let me move this
Fabulous.
up here. Let me just organize. Okay.
My throat is so dry now.
The beauty of teaching, right?
Yes.
All right. So, uh, going off of what Jordan was teaching just now, we're going to talk about how some of those things kind of relate to the body and balance. We'll be talking a little bit about the same brain regions as well as others, and kind of a lot of the same overlapping topics as well as new ones. But I want to start off this discussion by kind of uh, starting off with a general point, which is that everything that your body does is kind of a cycle. So there are cycles in the body in where things are promoted in a positive feedback loop, but those are significantly more rare as compared to the negative feedback loops. Um, and so we'll talk a little bit about how the stimulation of some of these hormones or cell signals can actually repress the signaling thereof by going back down the chain. So the more of something you produce, that'll physically slow down the release of that thing, and that way you don't get an overflow. So you want to kind of think of this input to output and then output to another input, and then everything's kind of yin and yang. So the idea of homeostasis is that everything is in balance. So in general, homeostasis is the tendency of the body to maintain the condition of equilibrium. You might think of, for example, a neuron firing. A neuron firing will change its membrane potential, but at some point that's got to return to the balance. What happens when a neuron does not return to its normal resting membrane potential? That's what we would call a seizure or epilepsy. So if you have a constant flow and things do not return to homeostasis, you get unwanted effects. So too much of something in this case is definitely not always a good thing. So depending on what the action is and what the end goal of the function is, will determine, what kind of cycles are going to go through and how the cell is going to communicate that to other surrounding cells, and therefore how systems of cells are going to react to certain stimuli and how tissues will contact or communicate with other tissues. Remember that when I say tissues, I'm talking about groups of similar cells, right? So nervous system tissue communicating with muscle tissue, for example, and vice versa. So the brain is actually, as we'll see, really responsive to hormones, especially during development. Uh, Levels of testosterone and estrogen and all these other hormones will play a role in the development of the brain. Um, and so the hypothalamus is kind of the superstar of today's discussion. The hypothalamus is just below, as the name implies. Hypo means below, thalamus. It's kind of telling you exactly where it is, just below the thalamus. It is really important for regulating your internal clock. Some of you may know we call that the circadian rhythm. But basically, when you know it's night, when you know it's day, and it's regulating the hormones that are secreted towards the endocrine system. So, in general, the endocrine system is related to hormone signaling and how that affects other tissues. So, for example, how often you urinate, how much you grow, how fast your metabolism or how slow your metabolism is. Um, but when that's connected to your nervous system, and it is, we would call it the neuroendocrine system. So, in large part, it's the neuroendocrine system. But let's talk a little bit about circadian rhythms. So, if you were to be locked in a room that was without sunlight whatsoever, your natural circadian rhythm would actually be longer than 24 hours. But we typically calculate our circadian rhythm or a circadian period within the natural 24 hours of the day, approximately. And all of this is dependent on how much you've slept, and really it's dependent on the light that hits your eye. So your retinas will play a crucial role in sending signals that, oh, it's daytime, There's a significant amount of light right now. I should be awake. And then when that sunlight goes away and diminishes over time, that will send a signal to your brain to secrete melatonin to put you into a restful state. So all of this is really coordinated by the SEN, which I believe was mentioned before, but this is the suprachiasmatic nucleus. I'll just shorten it for SCN for now. Um, and this function, although we kind of take it for granted, right, just waking up and going back to sleep, is really important for the regulation of a lot of our physiology. You may notice that if you don't get enough sleep, you are in a worse mood. So one of the topics we'll talk about is that this neural pathway affects your mood. It'll also affect how emotionally or how large you respond to smaller stressors. So your stress response. So that's related to cortisol. Cortisol is a really important hormone in this. It'll also facilitate other stress responses. Believe it or not, cortisol, we often put that into the group of stress in general. The stress hormone is cortisol, but cortisol is really important for a lot of things. So cortisol is known for breaking down tissues or being a catabolic hormone. If you have way too much cortisol for an extended period of time, so a chronic release of stress, that could be a bad thing. But in the acute phase, cortisol is actually really important for restfulness and arousal, to be awake, to actually wake up. And on top of that, it's really important for lipolysis, for getting rid of fat. So cortisol is a good thing in the right context and in the right amounts. But when we don't get enough sleep and when this suprachiasmatic nucleus for the SCN is disrupted in its function, that's when we get to difficulties. And so where people um, are less happy, they're gaining weight, for example, because their metabolism is down, their energy release regulation is out of whack, and you're at a greater risk of, especially as you get older, of heart attack, getting into a car accident, etc. So there's actually studies on this that when we set our clocks back an hour and we lose an hour of sleep, the amount of car accidents goes up and the amount of heart attacks go up. And so sleep is a crucial, often overlooked factor, and all of that is related to light entering the eye and that circadian clock. So what is and where is this DSEN? It's a tiny group of neurons in the hypothalamus. This is what I was mentioning before. Hopefully you can see my cursor, but this large kind of like dark brown structure is the thalamus, and just below it is the hypothalamus. And at the tip of this anterior superior portion, really inferior portion, anterior inferior hypothalamus is the suprachiasmatic nucleus. And you'll see that very close we have this structure known as the pituitary. And the hypothalamus and the pituitary are coordinated together to send signals as part of the neuroendocrine system. So when I mention the hypothalamus, somewhere in there is implied a signal to the pituitary and to other systems of the body. Another thing that I'll mention is that the hypothalamus is the regulator of, as I mentioned, the stress response. And that's part of a system called the sympathetic chain. So the sympathetic chain, which regulates our body's stress response, including heart rate, how much we breathe, and our breath rate, our GI organs, and how well we digest food and things like that. That's all regulated by the hypothalamus. So this is very crucial to your everyday life. So during the day, it emits a steady stream of action potentials, and they tend to quiet down at night. So that was the kind of initial finding that led researchers to say that this is important for restfulness and wakefulness. These states are controlled by cycling interactions of two sets of protein encoded by the body's clock genes. So like I said, it's not just a constant go. There's also an inhibition of that go, and that's what plays into that homeostasis. Okay. Now, one thing I'll mention is there's also been a lot of studies on people who work the night shifts and how that relates to stress, happiness, work-life balance, and their overall satisfaction with their job. And what they find is that those who work the night shift are typically, they gain weight, they're less happy, and at higher risk of other diseases. I'll do a kind of another point to this is that as someone who's going to medical school, something that you'll often hear if you're interested in medicine is the lifestyle of certain medical specialties. And there are specialties that require more on-call shifts. There are specialties that require night shifts. So for example, emergency medicine is one where you may have to do a night shift here and there. And that would require you to break that circadian clock. And that would essentially worsen your performance, but also worsen your mood. Another example is if you're a race car driver, or maybe you're a surgeon, or maybe you're, insert important job here. If you do not get enough sleep and are not wakeful and are constantly secreting cortisol because of that, your performance is going to decrease. If you're an athlete and you don't get good sleep, you're going to risk injury, physical injury, as well as decreased performance. So, all those things are related. When you wake up, one of the most important things to do is get sunlight, is to turn on the light. You'll notice that if you turn on a light, you'll wake up more quickly. Whereas if you stay in a dark room, you'll tend to continue to be tired. Okay. And like I mentioned before, it takes a little bit more than 24 hours to complete a full cycle, but this is all stimulated and changed based on exposure to light. Now, another really important structure is the paraventricular nucleus, or the PVN. This is a region that's stimulated by the SCN. And then as mentioned before, or actually before I go down that road, it signals down a chain of neurons through the spinal cord to the peripheral organs of the body. This is part of that sympathetic chain that I was discussing, which actually has a whole set of ganglia that go down uh, essentially parallel to your spinal cord and your vertebra, your vertebral column, and then out to the organs, to prevertebral ganglia and to organs, and that'll regulate your GI, it'll regulate your heart rate and so on. Signals in this part of the neural pathway stimulate orexin neurons. Another name for orexin neurons are hypocretin neurons. They play a role in the same sleep and wake cycles, in the same cycles for energy homeostasis, in feeding behavior. So if you do not get sleep, you'll notice that you are more prone to make bad decisions about food. So if you look at literature for nutritional sciences, you'll notice that those who lack sleep make poorer food choices and therefore gain weight quicker. And that's also not including the energy balance issues that occur with along with that. Now, those same related pathways are the ones that you may have heard of that are related to melatonin secretion. Melatonin is a hormone that plays a role in our brain that influences our tiredness and our ability to go to sleep. It reduces alertness. And you may have heard of supplementation of this. You may have heard of people taking melatonin as a supplement. And while there is a time and place where that might be necessary, there's also kind of contrary opinions about whether or not this is a good idea. I believe there was a study that showed that people who took melatonin long term had a smaller pineal gland, which is the typical gland that secretes this hormone, which makes sense because many of our hormones are regulated by negative feedback loops. So if you take a hormone exogenously, as in like a pill, and it's in your blood system, in your brain, your body is going to be inhibited from making that hormone because you already have plenty of it. And therefore, that organ or gland is not going to get stimulated as often, and therefore it will atrophy. There's a comment, I think I used this in the last lecture too, that I did, is if you don't use it, you lose it. So in this case, the pineal gland won't be secreting this hormone, and so therefore it won't be needed, and therefore it will shrink because you're not using it, so therefore you will be losing it. So the alternative method of supplementation would be something that helps decrease the I guess you could say counteracts the effects of caffeine and helps you go to sleep by depressing neuronal behavior, by getting you to that reduction of alertness. And one of those ways was through magnesium, which is an important ion that many people are lacking. And it's actually also related to epilepsy. Something that we do in our lab, or we were running a project in our lab, was magnesium loaded nanoparticles, or magnesium nanoparticles, those are different, to depress the alertness or stimulate inhibit the stimulation of neurons by blocking calcium channels and so on. And so there's really important signaling pathways there that you can manipulate neuronal function and therefore even influence diseases and other conditions and even injuries. So think twice before you take exogenous hormones, not just related to melatonin, but other ones as well. Circadian rhythm disbalances. So a common example of this is jet lag. You may have, if you've gone on a long trip across the country. I'm from Colombia, so that's really kind of in the same time zone. But let's say you go from where we are today to the other side of the world. Maybe you're visiting China or India or even Europe, Africa, whatever it may be. You're going to change the time frame in which you are exposed to light and exposed to darkness, and that's going to change the pattern in your brain of when you should be awake and which you should be sleeping. This recalibration of the clock may take some time. And this can also lead to other problems, as discussed before, which would be weight gain, feeling like you can't fall asleep, and also some mood changes. Some of this has also been associated with cancer. And that has to do with regulation, immune function, and uh, um, energy homeostasis. So when you lose sleep and you don't get enough sleep, um, not only are you throwing these things out of whack, but you're depressing your immune system. And so that could flare up things. So one of the, uh, you may have heard that, for example, the chickenpox virus stays dormant in your nervous system over the course of your life. Well, if your immune system is down, you may be exposed to the development of shingles, which is a recurrence of that virus on your skin, which can be painful and can cause discomfort. For me, I suffer from something called seborrheic dermatitis, which Jordan will laugh at because I've had a really bad day today on my face. And part of that is because I didn't get good sleep the last 2 nights and the weather changed. And so we went from hot and humid to cold and dry in Florida, at least the last 2 days. Um, and that I think played an important function in my face. So losing sleep can depress your immune system. That depression of the immune system can lead to other things, for example, the development of cancers. All right, melatonin secretion. So this is the structure of melatonin. I want to point this out. When I was your age, I didn't really care for the chemistry, but understanding the shape and chemical nature of these hormones is actually really important, especially if you're trying to make drugs that mimic those hormones but don't have the negative inhibition side effects, which is a huge area of research for the supplement industry as well as the sports industries. If you and even military, if you can get your soldiers to sleep better and perform better without having the negative side effects of those things, that might be very interesting for research. Um, and that could mean funding. And so there's a lot of reasons to pay attention to these things. You may see this hormone here and be able to build something that's similar to its shape and structure, but different enough that it doesn't cause the same level of negative side effects. So, pay attention to the structure. Notice how cyclic it is and this carbon chain with this nitrogen group in the middle. Um, just pay attention to it. Be aware of it. Be familiar with it. I'm not going to ask you guys to necessarily remember the whole name. Maybe I will. I don't know. But be aware of that. So light will inhibit the release of melatonin. So this is why you may have heard the tip: if you want to go to bed better, turn the TV off maybe an hour before you go to bed. Don't scroll through Instagram like Jordan and I do on our phones before bed. Don't answer emails right before bed. Don't do work right before bed on your screen, like write the essay that you should have written over the weekend. um, get your restful sleep because it'll hurt your performance if you don't. Lack of light is what actually would stimulate the release of that. So you'll see the suprachiasmatic nucleus. Once this light does not hit the retina, you will see that this. By the way, I'll actually ask you a question here. I know there's no students currently here, but what nerve is this? I'll give you. You can pause video right now. But what nerve is this? Which cranial nerve number is it? Pause right here. So this is the optic nerve. Is cranial nerve 2. And that is going to send a signal to the SCN, which is your biological clock, which will send other signals that will eventually make it to the pineal gland. Notice that it goes down through your spinal cord first as well, but it'll go out to your pineal gland, which will secrete this melatonin, which will stimulate your brain or inhibit that, essentially, the stimulation of your brain. The other thing about the pineal gland is actually situated right in between posterior of the hemisphere. So this region right here in the back of this brainstem, this would be near the cerebral peduncles, essentially. This is the pineal gland is in the center of both hemispheres. It's actually just one little blob. Okay, right above the cerebellum, right above the quadrigeminal plate or the corpora quadrigemina. These two structures are related to sight, and the bottom one here is related to hearing. But just above this, the full structure corpora quadrigemina, above it is the pineal gland. So that's I find an easy way to find it. And then right below the posterior inferior end of the corpus callosum is another way you can kind of find the pineal gland. Okay, so moving on from there, preparing to wake up. So when you wake up, levels of cortisol, the stress hormone, peak in the blood, releasing sugar from storage and then increasing appetite. This is when you're kind of waking up for the first time. There's actually some controversy here about whether or not you should take caffeine immediately upon waking up or if you should wait for a little bit, because taking caffeine may disrupt this cycle of cortisol production and enhance how dependent you are on caffeine. Please hold as I take a sip. Do as I say, not as I do. Two, the core body temperature begins to rise. So another not so well known aspect of sleep is that in order to fall asleep, your body temperature actually has to decrease. But in order to wake up, your body temperature actually has to increase. So it's easier to fall asleep in a colder room than it is in a hot room. And I find this out every time I go visit my parents, who keep it at 74, 76, up to 76 degrees. I can't do that. I sleep at maybe 70, and I have friends that go all the way down to 68, and that's a little cold for me. But a cold room is easier to fall asleep in, and that's because part of that process requires you to decrease in temperature. All right. So neurons versus hormones. This is very interesting. So there's actually different kinds of hormones. There are peptide hormones, and then there are steroid hormones, which are derived from cortisol. Something like testosterone is derived from cortisol. These are hydrophobic large molecules that have 8 typical cyclic portions to it, whereas a peptide hormone like insulin is smaller and will have an effect outside of the cell, whereas something like testosterone will actually enter the cell. But neurons can either stimulate the release of hormones, or they can send signals in a different way. The benefit there is that neurons can send a message pretty quickly. We've already talked about the reaction to a very hot stove or something sharp, right? You have this acute, innate sense to remove that stimulus without even having to think about it. So it happens 180 meters per second, I believe, is the maximum speed of a myelinated motor nerve fiber. So that's a very quick message that can be sent. It's a boop, done. Whereas hormones deliver messages way more slowly. It's over the course of time. So for example, when you eat a French fry, it takes a couple minutes for that sugar to become available and then for your insulin to rise. And that could rise and continue to be steady depending on how much carbohydrate you consume. On the flip side of that, if you were to so for example, if you wanted to send a signal to your muscles to grow, this is why some bodybuilders would illegally use steroids, like testosterone, is because they wanted to send that message over time to say, grow, grow, grow. But that is a slow process. It takes time. It's cyclic based, so it fluctuates in our typical lifespan. We go through periods of where things are high and periods of things that are low. So to give you another example of hormones, testosterone is very high in men, in particular in the teen years when they're growing and maturing. But even now, as an adult, for example, there's studies that show that you can increase and decrease testosterone depending on your habits and depending on if you're lifting very heavy weights, depending on how much force you exert, etc. Now, back to neurons. Neurons in your brain listen to those hormone signals, whether it be testosterone, melatonin, or whatever it may be, to regulate the function of our physiology. So if there's way too much of something, that will likely inhibit the production of that thing, and actually increase the opposite of that thing in order to reach homeostasis again. Um, so this listening and constant, fluctuation of yes and no's, go and stops, is what keeps us in equilibrium. All right. So let's talk a little bit more about the role of the hypothalamus. So it oversees the production and release of many hormones. Just like I mentioned before, it'll release gonadotropin releasing hormone, um, corticotropin releasing hormone, um, and many other ones that are related to metabolism and whatnot. The PVN and the SCN of the hypothalamus send axons to the posterior part of the pituitary glands. And the activation of specific neurons initiates the release of either vasopressin, which is antidiuretic hormone, or oxytocin into the capillaries within the pituitary gland. These are hormones that we'll talk a little bit more about in a second. And then there's other ones. So another in case I think I did mention it before, this axis is known as the HPA. So if you ever hear HPA, the hypothalamic pituitary adrenal axis, it's discussing the connection between the hypothalamus and the pituitary, which are very intertwined as it relates to the neuroendocrine system. So vasopressin, or antidiuretic hormones, you might see ADH is the abbreviation here. The hypothalamus will send a signal to the pituitary, specifically the posterior pituitary. That'll release vasopressin, which will stimulate your adrenal gland, and that will secrete aldosterone. So I would recommend that for you students at home, you make a flow sheet of this. You have posterior pituitary releases ADH. ADH to the kidney and adrenal gland that secretes aldosterone. This has an effect on the kidneys, which will lead to diuresis, or the vasoconstriction of the blood vessels there. Okay. So antidiuretic hormone is what it sounds like. A diuretic is something that essentially allows the release of urine, whereas antidiuretic tells the kidney to retain water. All right. So the next hormone is oxytocin. This is a really cool one. So like I mentioned before, take a look at this incredibly large and complex structure. There's cycles there. If you know your amino acids, you can kind of pick out where these are likely derived from. It's kind of like tyrosine group, this phenolic group. This looks like a guanidino group, which might have come from arginine. All these different cycles and stuff. Notice how complex it is. These hearts are added for your viewing pleasure, but they don't actually exist there. But this is a neurotransmitter in the brain, but it acts as a hormone elsewhere. So its function is to promote uterine contractions during labor. This is actually one of the few positive feedback loops. So this will actually increase over that time and then stop suddenly afterwards. And it also promotes the milk release during nursing. Many people will call oxytocin the love hormone. So when you hug a loved one, your oxytocin goes up. And it can also help regulate mood and related neural pathways. So oxytocin is very important, obviously, for labor, for milk production, but also for feeling connected with your family, brothers, sisters, etc. Okay. So like I mentioned before, when neurons are activated, they can release hormones or stimulate the release of hormones, which will have an effect elsewhere. Remember that your nervous system is like this giant computer that regulates all the other organ systems in the body. And there's a lot of research that is coming out that's showing that simply stimulating the nervous system in a very precise way can induce the physiology or the phenotype that you wish to induce. So for example, you can reduce inflammation by stimulating or inhibiting certain neural pathways. And so you don't even have to take a drug. So there are people who are working on this that are trying to reduce the need for pharmaceutical grade or pharmaceutical drugs and replacing them with devices that stimulate or inhibit the nervous system. So that's something that I just wanted to bring up to your mind, because the nervous system is a powerful thing in terms of regulation of bodily functions. And you can do a lot when you know a lot about how to control the stop and goes of this. If you can understand all of the neural pathways, whether or not a hormone is released, how much of it is released, how much of it is inhibited, you can control different reactions and essentially control diseases that way. For example, diabetes. You can control, depending on which kind of diabetes, obviously, because there's a lot of nuance here that we're not going to have time to get into, but you can stimulate or reduce the stimulation of the release of insulin and other hormones, maybe testosterone, for example, or estrogen or anything like that, to get the desired effect that you want. And that would have to go through the bloodstream. So the neurons would release it, but then the hormones would have to travel through the bloodstream. Okay. In the anterior pituitary, they trigger or inhibit the secretion of a second specific hormone. So this is called tropic hormones. You will often have one hormone that begins the pathway, but a hormone that stimulates the release of a different hormone that will go and have the effect is actually called a tropic hormone. So there are hormones that will be secreted as they are, and then there are hormones that will stimulate the release of a different hormone, and that's what we would call a tropic hormone. Okay. So these are some very important hormones that you should know. So adrenocorticotropic hormone, ACTH, thyroid stimulating hormone, TSH, which would stimulate the release of specific thyroid hormones. Follicle stimulating hormone. This is very important for the menstrual cycle and the growth of the follicle. Prolactin, growth hormone, all of these things I would recommend writing down and knowing their abbreviations. These are things that we can quiz you on the exam. So for example, we can say, which one of these is not one of the hormones secreted by the anterior pituitary? So there's like a typical style question. I'm not saying that that's exactly what we're going to ask you, but something to think about. And then there are 5 trophic hormones. These travel through the bloodstream to stimulate activity in a specific endocrine gland. So for example, TSH would be in this category, right? So if you send TSH, that will stimulate the thyroid, but the thyroid is going to release specific thyroid hormones, which will have the effect elsewhere on the body in regulation of metabolism and so on. The ACTH, adrenocorticotropic hormone, for example, will also lead to the release of cortisol or something else through the adrenal cortex. So those are kind of important pathways to jot down and have a flow sheet of. And the function of all of these is to influence growth, metabolism, but also everything else. So something that's often overlooked in these neural pathways is also the way that you're feeling because of it. So if any of these things are dysregulated, for example, like I mentioned before, if you have less sleep will lead to more or less secretion of this or stimulation of the secretion of a specific hormone that will change how you behave as well as what choices you make, which would drive up your hunger, maybe decrease your hunger. That'll affect your weight. It'll affect your ability to do exercise. It can affect, if this goes long term, it'll affect how much calcium's in your bones, for example, leading to osteoporosis. So imagine that you keep this acute sense, right? So something's happening right here, right now. But over the course of time, if those things remain constant, which they can, then that would lead to something else in the long run. And so understand the relationship between these pathways and what they secrete and what their function is. What is the outcome of it, so that you can understand eventually how those outcomes, if they go unchanged because of habits or conditions, that they would lead to an undesired outcome. Okay, so chronic disease, for example. So more on hormones from the pituitary that target endocrine glands. So affect receptors inside the brain altering neuron functions, and gene transcription in the hypothalamus reduces the amount of hormone released by the hypothalamus when circuits become active. Yeah, so this is going back to the negative feedback loop. So the more of a hormone there is, the less of it will be secreted in order to maintain the concentration that's desired. That way, let's say, for example, that melatonin made you really tired, but if you had no way to stop the secretion of melatonin, nothing inhibiting that, then there would be nothing to get you awake because you'd just be stimulated to go to sleep. So there's always something that's going to have a limit, and then things will naturally decrease after that because you're inhibiting those neurons. Okay. So three hormone cascade, the regulation of production. So the underlying process is the same for both. So gonadotropin releasing hormone, GnRH, that's secreted from the hypothalamus, and that causes the release of luteinizing hormone and follicle stimulating hormone. These are important in the menstrual cycle. They're important in females. They're important for both sexes, but in the female, it's very important in terms of the menstrual cycle. Maybe at one point we'll have like a discussion about that as well, more specifically. Luteinizing hormone and follicle stimulating hormone, they cause the gonads to secrete the sex hormones. So if regulation of testosterone would happen in this way. So you can imagine that if this was, if the negative feedback loop was applied to this, if you had too much testosterone or a significant amount of testosterone, whether it's because you're supplementing with it, if there's a pro bodybuilder, sometimes they do this, that would block the release of luteinizing hormone and FSH, which would eventually slow the release of your body's natural testosterone, quote unquote, natural testosterone, your testosterone that you would produce. And then that would cause your gonads to shrink. Same thing, ovaries. If you're taking exogenous hormones, that would lead to that organ that produces it to shrink. So keep that in mind. These sex hormones, they start the development of mature eggs or sperm. They attach to receptors in the hypothalamus and anterior pituitary and modify the release of the hypothalamic and pituitary hormones. So those hormones go back up to the brain and will signal, hey, we're here. You don't need to make more of us. Or they'll signal, whoa, we're here. And then the brain just continuously gets that signal, and then you really inhibit it. Or they are not present. Therefore, those receptors are not stimulated. Therefore, the underlying process will get upregulated because there isn't a sufficient concentration. And that's why when you look at blood tests for these hormones, there's ranges. So there's ranges of how much is naturally produced by a body, depending on the person, depending on that person's body mass, depending on certain aspects of their habits and obviously genetic factors. All right, so the male sex hormones. Yeah, so I kind of already mentioned this. You can kind of read this on your own, but essentially having that would reduce the secretion of GnRH. Yeah. So for the female sex hormone, this is in cycles. So the menstrual cycle we know happens, let's say, for the course of about a month, and that would increase. And there's actually fluctuations in the amount of GnRH and also LH and FSH and what it does in terms of the development of the follicle, and whether or not the woman will experience the period or whether or not she's going to get pregnant, depending on the context. But the rising of estrogen of these levels, so this is an important bullet point. Rising estrogen levels cause luteinizing hormone to rise, exerting a negative feedback on the follicle stimulating hormone. And this is an important inhibition so that it limits the number of eggs that can mature in a month. Different between the sexes is that males will continuously produce sperm throughout their lifetimes, but when females reach their maturity, they have a finite amount of eggs, and so they will reach a point where they can become postmenopausal, and then they can no longer get pregnant because they don't have any more eggs. And so this inhibition allows that period of reproduction to be extended, which was important for the survival of our species, et cetera. So this is how kind of these hormone negative feedback loops apply to us, not just on an individual level, but how the potential of our species can continue or not. So that's why it's important. All right. Specific tissue hormones. So released by specific tissues that are not necessarily regulated by the pituitary gland. The brain contains receptors for these hormones, but indirectly regulates their secretion. So leptin and ghrelin. This is really important now because of some of the medications that have come out that regulate hunger and affect receptors that essentially affect the ability for someone to want to, their desire to eat. So leptin and ghrelin. Leptin is a hormone that essentially stimulates hunger. Ghrelin is, or no, sorry, I might have that flipped. But these hormones essentially regulate your hunger or whether or not you're feeling full. And what's really important about this is that these hormones can also be regulated by your gut. So whether or not you've had enough to eat, the microbiota in your intestines can actually influence how much of these hormones are produced and can stimulate or inhibit your hunger signal. And a lot of these new drugs like Ozempic and essentially semaglutide affect your brain. And this is both good and bad. It's good because it means that we are getting closer to understanding the exact kind of mechanisms behind obesity and the desire to continuously eat and all that stuff. But it also means that there are potentially ways to increase that signaling pathway without the use of drugs in certain contexts. And one of the ways that researchers have hypothesized is through regulation of your gut bacteria. Your gut bacteria will essentially influence this pathway naturally. And people who are obese and even people who develop Alzheimer's, not that these are necessarily exactly the same and related, but changes in your gut microbiota will influence your brain. And that has had implications in Alzheimer's as well as Parkinson's, which I know we're not necessarily talking about here, but to kind of stimulate your brain into kind of the weirdness that the brain is and the gut brain axis, there are studies showing that you can transplant fecal matter between healthy rats and Parkinsonian diseased rats, so Parkinson's disease rats, and you can reduce some of the symptoms because of the changes to the gut microbiome. Which fecal transplant means that you take the fecal matter out of one mouse and then you put it up into the other one. And believe it or not, that has a physiological change on the entire rat. So, these signaling pathways are important to understand for that. Okay, so here's a little bit of clarification. So ghrelin, I remember now. Ghrelin is like grr, your stomach is growling. So that's I should have remembered that. Ghrelin is like your stomach growling for food, whereas leptin decreases appetite. So kind of counterintuitively, but also in a deeper sense intuitively, when you have a large meal full of carbohydrates, your leptin actually increases, thus decreasing your appetite. And you're actually best posed, for example, to reduce your fat stores after you've had a healthy meal. So one of the strategies that we employed or that I employed as a personal trainer is not necessarily to eat less, but to eat adequately and exercise more. So it's not necessarily about starving yourself. It's about exerting energy throughout the day, whether it be through exercise or non-exercise activity. For example, just going, well, I guess this is still exercise, but going up the stairs instead of taking the elevator, or parking far away from the store instead of parking as close as possible. These kind of things throughout the day, sitting up straight, standing up when you're working, increase your caloric expenditure. But that way you don't have to eat less. You can eat the same, but you would be expending more. Therefore, you could burn fat off of your body. But these, hormones play an important role. And so understand what their function is, where they come from, and kind of that relationship. So leptin is actually produced by your fat cells and is released when the fat stores are large. So this is kind of the counterintuitive thing, is that uh, leptin is stored in fat and released when you're essentially plentiful of energy. So your body has evolved to say, I need energy. I can't afford to expend it right now. And then when you get that large amount of energy, you're feeling safe. You're saying, okay, I have energy. I can expend it now. That's why we have large fat stores. Okay. As fat cells are used up, leptin levels decline. So this is kind of a driver of the phenomena that as you get leaner, it gets harder and harder to progressively get leaner and leaner. And you'll hear this from professionals who their job is to get very, very thin for photo shoots or for competitions. It's the last like 5% body fat, which is really difficult to lose. So if you're at 10% and you want to get down to 6%, that's the hardest. And it's unhealthy to be super low for most people. So that's kind of like one of the limiting factors. It's always hard to lose that last little bit of fat. But the leptin will also bind to neurons in the hypothalamus to suppress the activity of hunger circuits and reduce the desire to eat. So these are the signaling pathways that essentially some of these new drugs are trying to take advantage of. Can we talk to the brain without signaling of food? Can we bypass that signal to tell the brain, hey, we're full, we don't need to eat, and therefore decreasing the caloric intake, and therefore being at a caloric deficit and losing body fat, that energy store instead of the consumed energy. Okay, so if you have no background in this, you are burning some amount of calories. Let's say it's 2,000 calories. That'll fluctuate, but to make it easy, about 2,000. And if you tell your brain to eat less and now you're eating 1,700 calories because you're not as hungry, you are now at a 300 calorie deficit over the course of 7 days. That's 2,100 calories. And that's not as much of a pound, but that's slow weight loss over the course of time. So if you do this kind of mathematics and you keep those habits steady, you could lose a lot of weight in the course of many weeks to months. And that's essentially what bodybuilders do. They consume excess to gain weight, and they consume slightly less to lose weight. But that's a consistent thing. Okay, so let's talk a little bit about stress, even though we already have for a little bit. So this is something that has evolved to aid us to run away from dangerous stimuli or dangerous feeling stimuli. Stress acutely is a good thing. So exercise is a stressful thing. The exercise and using your muscles leads to inflammation, which is actually a good thing. So understand the differences between the acute sense and then the chronic sense. Chronic, something that's acute, it can be good, but bad when it's chronic. And so this stress response is normal to wake up and then hear your alarm clock and all of a sudden you're like wide awake, your heart rate goes up and whatnot. So this has been evolved to keep us safe. So whenever you feel threatened, whether it be the alarm tone from Apple, or some loud noise at a restaurant that makes you turn your head, maybe someone dropped a plate or dropped a glass and it shattered. You're like, that stress response has been there to be like, oh, what is that stimulus? I need to be aware of it. That way I can run away from it if I need to. And we all know that kind of response, right? So our heart rate increases, our breath rate increases, our muscles get tense. It's because it's like an engine preparing to move. If you've ever seen a drag race between two like cars, or maybe even an F1 race at its start, the engines are essentially getting to an RPM so that they can produce energy maximally within their power band. In the same sense, we are breathing in more oxygen, which is an important aspect of the combustion of this energy so that we can produce ATP. And our heart rate increases, therefore increasing the amount of oxygen that can get delivered to the muscles, so that we can move quicker. This is why, as a personal trainer, when we want to begin exercise, part of that exercise warm up is getting your heart rate up, getting your breath rate up, and getting your body temperature up. And this is not only improving performance, but obviously it's reducing injury. So this is a mechanism that we've evolved to do such a thing. Okay. So the stress response involves both voluntary and involuntary things in case you haven't noticed that just yet. So your heart rate will increase without you caring for it. But then also voluntary is like running away or fighting back if you have to, those kinds of things. So voluntary muscle, involuntary muscle, the sympathetic nervous system will coordinate that as well. All right. Yeah, so a lot of this is happening autonomic and then also somatic. So when you think of somatic, think of muscles, think of priming, essentially being able to do the task. And then the autonomic things are things that are out of your control that are priming you, preparing you to do those things. And again, a lot of that driving factor has to do with nutrient delivery, oxygen delivery, anything that allows you to break down something for energy production so that you can get out of the harmful way of whatever stimulus it is, whether it be a lion or an alarm clock. It's kind of the same response both times. The sympathetic branch. So this is the sympathetic chain that I was talking about. One thing that this image is kind of missing is the connection to the hypothalamus and pituitary. This will signal down, but throughout your spinal cord, you'll have the sympathetic fibers synapsing with these paravertebral ganglia that will eventually synapse with these prevertebral ganglia for some of them, and coordinate the secretion or inhibition of certain aspects. So, for example, these are called the splanchnic nerves. There are splanchnic nerves that regulate your stomach and your GI. There's the greater, lesser, and least splanchnic nerve. You have your cardiopulmonary splanchnic nerves, which will stimulate, your heart rate and other things. Um, and then you have the parasympathetic parallel to this, which is doing the opposite. Oh, here, this is the other one. That's the vagus nerve. So these are kind of like running in parallel, and again, a little bit antagonistic to each other. Sometimes they work in coordination, but oftentimes we think of sympathetic and parasympathetic as inhibiting each other. They're kind of like yin and yangs of each other. So while the sympathetic is up and running, the parasympathetic kind of takes a back seat, and it'll eventually regulate itself by inhibiting. When you think of sympathetic, think of stress. So your heart rate goes up, breath rate goes up, blood flow and movement in your bowels is reduced. Your bronchioles actually relax and open up, so they dilate to get more air. We release epinephrine or adrenaline into our system. The parasympathetic branch is a little bit different. So the parasympathetic branch will restrict the blood flow to the organs like the skin, the gonads. So things that, in terms of the things that you're not going to need the blood flow to at the moment, it'll reduce that. And then the opposite is true. So if you're not stressed, you can digest. So you may have noticed that, I don't know if this has ever happened to any of you if you're student athletes, but I remember I ate lunch pretty late one day before basketball practice, and we were running laps at the track, and I maybe had like a chicken wrap or something, and we started running real quickly. I didn't get to warm up as well as I wanted to, and you vomit. Like your body's just like, get rid of this. I need to get rid of it and then go, because you're so stressed. Whereas if you weren't stressed, if you were just relaxing, you could just continuously digest, and the blood flow is where in your intestines, and you're absorbing all those materials. So understand for the exams the roles and the differences between the sympathetic and parasympathetic nervous system. Understand what regulates them. So for example, sympathetic, you should immediately think hypothalamus. For the parasympathetic, you should immediately think vagus nerve. Question is, which cranial nerve number is the vagus nerve? And then the answer, 3, 2, 1, cranial nerve 10. So, or cranial nerve X, which is labeled here. So cranial nerve 10. So understand kind of those details that can come up on the exam. All right. A couple more slides. I'll kind of breeze through these to not take up too much more time, but the glucocorticoid hormones are a cascade of neuroendocrine hormones from the hypothalamus and anterior pituitary, which circulate in the bloodstream. They affect metabolic rate, sexual function, and tell the adrenal cortex to release glucocorticoid hormones like cortisol into the blood. Even more, so we're actually not diving too deep into the adrenal gland, or the suprarenal gland, as it's sometimes called, which sits just above your kidneys. But there are actually different sections to this. There's the medulla and there's the cortex. The cortex is this outer shell. The cortex and the medulla will actually secrete different hormones. But cortisol, again, is really important for these things. And then regulating metabolism and sexual function are really important aspects of the glucocorticoid hormones. So this is another one of these flow charts that I would recommend writing down. So the PVN, your responses stimulate here. They go down through the hypothalamus into the pituitary. Then we have a releasing hormone, or one of those trophic hormones, leading to the adrenal gland. The adrenal gland will actually get stimulated from this trophic hormone and then secrete the actual hormone, which is going to have, I shouldn't say actual hormone, the secondary hormone, which is going to have the intended effect on the body. This will also have a negative feedback loop on the pituitary as well as the hypothalamus, saying, if there's a ton of cortisol released, this is the limit. Let's stop secreting that. Okay. All right. Again, another important thing about cortisol to remind you is that it's important for attention. It's important for learning. It's important for burning fat. It's important for a lot of our normal physiological functions. Don't necessarily think that cortisol is bad. think that cortisol has a specific function, and too much or too little of that can lead to unwanted physiological outcomes. And then here's where we talk about chronic stress. So this slide and one more. We can't really differentiate between levels of stress. Signals are just signals, and then that would lead to, again, that physiological effect, and having too much of that can lead to bad things. Chronic stress causes one's adrenal glands to keep pumping out epinephrine and glucocorticoids, and can be detrimental to one's health. We know very well that chronic stress is dysregulates your heart rhythm, your sleep rhythm, your entire circadian clock. It can lead to inflammation in other places. It can lead to cancer. It can lead to um, decreased immune function, etc. So, keep that in mind. It's kind of the overall tips is to sleep well, eat well, and take care of yourself, and not overdo things. Have a timeline. We're all kind of on our circadian rhythm, so getting out of that circadian rhythm will negatively affect those pathways. And I'll let you read this slide on your own time, but I think those are the kind of the big points. As a general overview for this is understand the regulations of these patterns, the hormones, the pathways of these hormones. Understand that most of them function in a negative feedback loop kind of manner. Which ones function as a positive feedback loop manner? That might be an interesting thing to note. How does dysregulation of these pathways affect someone or affect their physiology? Why and how? How does this PowerPoint relate to what Jordan taught us earlier in terms of sleep? For people who deal with narcolepsy, for sleep apnea, for all these other conditions, how does that relate to hormone function? And how does that relate to what's happening at the cellular level? And then more importantly, how does that affect the lives of real people? And what is a possible intervention? So, for example, sleep apnea reduces a person's ability to get deep sleep. Not getting adequate amount of sleep as well as balanced sleep, so going through all the sleep cycles, will affect their brain waves. And if you were to read that on an EEG, you would see dysregulation. How does that affect their cortisol levels? How does that affect their growth hormone levels? And if this happens over the course of time, how does that affect their physiology, and what can happen in the course of that due to having sleep apnea for many years? And then the last question is, what is an intervention? So what can you do to um, improve that outcome for someone? So that's kind of the whole purpose of research in medicine. So I'll give you this last example. This will be the last thing I say, because I know we went a little, it's getting late for us too. But obstructive sleep apnea, something gets in the way of the airflow, maybe allergies or bone spurs in the nasal passage. Air doesn't really flow very well through your nose or through this patient's nose. Therefore, they don't sleep well. And this happens for many years. So let's say 10 years, they've been dealing with this ever since they were a child. And this has caused them to wake up drowsy, sometimes even disoriented. They have the question I could ask you is, what kind of symptoms do you think this patient would have? They're not getting enough oxygen in their sleep, so their neurons have actually become, some of them, the brain cells have become hypoxic because of a lack of oxygen, which is very dangerous. This lack of sleep increases the release of cortisol. Stress hormone goes up. What does that have to do in terms of the functions of your body? Well, your mood and behavior is going to change. Your appetite is going to change. There's dysregulation. So as someone who has dealt with sleep apnea, I can tell you that you're going to want to sleep more. You're going to be drowsy. You're going to make bad decisions for food because your body is stressed and it feels like it needs something quickly. So you're more likely to reach for that donut instead of a piece of broccoli, to give you a really exaggerated and bad example. Never would I ever reach for a raw broccoli, but maybe you do. I don't know. The point is, you're going to make worse decisions. And then what are some possible interventions? So for someone who has obstructive sleep apnea, one of the ways that you can reduce that is to reduce what's obstructing the airflow. And a CPAP machine can help do that for certain cases. Another thing is a septoplasty, turbinoplasty, which is where a surgeon will actually open up this passage of the patient's nose and then will essentially make room surgically in the nasal airway. And then that will help open up that over time. Um, a possible intervention that I was looking into was actually the nanoparticles that deliver cytoprotective compounds. And so, can you, at the very least, reduce the negative effects on brain cells using nanotechnology or some drug to offset that sleep apnea somehow? Um, that's a research thing, but the surgical technique is already being used. Um, Another thing that can cause sleep apnea is excessive weight gain. Excessive weight gain can lead to sleep apnea, which can lead to those symptoms. And so, these all of these things are interconnected in one way. And so the goal for you guys is to be able to integrate that, to say, this is the hormonal pathway, these are the diseases, and this is how all of it plays together to form someone's life and someone's well-being, and these are the challenges that we face ahead. So for narcolepsy or sleep apnea or chronic stress or all these dysregulated pathways, what is something that we can potentially do to make those people's lives better? That's kind of the end goal. But I will leave you with that. I don't know if Jordan wants to say anything else in terms of what you should study for and exams. Focus on big picture things, focus on pathways, and again, focus on interventions and how to put the big picture together, I think is the most important thing.
That was fabulous, as usual, Sebastian. I just want to thank everyone who has made it this far and stuck along with us. Again, please, please, please feel free to reach out with any questions you have or concerns. We are here to help you guys, and we are so excited that you are going to be participating in the Brain Bee. And we look forward to talking to you next month.
Perfect.
Have a good
Bye,
evening.
everybody.